This is Professor Stugard, and in this video, we're going to go over some definitions for our data. So, at the end of this lecture, hopefully we will have reviewed some of our definitions from statistics, because again, our definitions for data are the same definitions for statistics. Doing statistical analysis is actually the same thing as data science. We're also going to review what it means to have a tidy data set, and then we're also going to review some of the basic R functions and commands that can help us to understand a data frame before we do any sort of in-depth analysis. So let's jump right in with some of our definitions. And again, hopefully this is a bit of a review. Hopefully you've seen these before in a statistics class. But the first definition we're going to look at is univariate. So uni, right, means one, and variate means variable. So it just means that there's one variable. If I'm looking at univariate data, that means there's just one variable and that's it. So, for example, if I decided to collect some data on the different color of cars in the parking lot and went out there and just started tallying the different color of cars, well, that's univariate. All I'm looking at is one type of variable, which in this case would be the color of the car. All right. And again, univariate, that's a really, really good way to sound smart and use jargon. That's actually an incredibly simple idea. Then we have our bivariate data, and again, the prefix bi would mean two. So in this case, we are looking at the relationship between two different variables. Then we also have multivariate. So multivariate would be if we have a bunch of different variables and we want to compare those different variables and see if there's some sort of relationship between all of these variables. But in practice, typically what we do is we're actually going to just look at only two of those variables at a time. We're going to take all that multivariate data and then just separate it to do two at a time. One of the reasons being is that, again, a lot of times we like to use, graphics and create plots and graphs of our data. And when we pick just two variables, well, that makes a nice coordinate plane, right? We can look at how two variables are related to each other on graph paper. Pretty simple. However, if I was looking at seven different variables in my data at the same time, I would need a seven-dimensional graph. So what does a graph look like in 7 dimensions? I don't know. I have no idea. That's crazy, right? I can't possibly fathom what 7 dimensions looks like. So again, typically when we do our multivariate data analysis, what we're really going to be doing is focusing on just two of those variables at a time. Now, when we talk about variables, we want to make sure we understand what type of variables they are. So we have quantitative variables, which would be numerical, right? Quantitative, quantity. What is the numerical value of these variables? And when we have numerical variables, right, variables that actually take on numbers, we can either classify those variables as either being continuous or discrete. Continuous means that those variables take on any value in the continuum. So for example, if I was measuring length or distance, right, how far apart are my fingers? All right, they're 9.672543 inches. Well, if I can keep doing that, if I can keep extending my decimal places as far out as I want, well, that's a continuous variable, right? And it can take on any value. I can keep getting closer and closer, and it can take on any possible value. That's typically what we call continuous. The other one is discrete. So discrete means, well, it can only take on discrete values, which typically would be our counting numbers. It would have to be our counting numbers. So, for example, if you were asking students how many classes you're taking this semester, well, that would be an example of a discrete variable, because you're either taking one class or two classes or three classes or four classes, but you're not taking 2.78543 classes. That doesn't make sense. You're either taking the class or you're not. The only way to count those would be with discrete counting numbers. If our variables are qualitative, right, which means categorical, which means we're basing them on our qualities or our categories, and it's not a number, although you can have numbers that are actually categorical, like your phone number, because it has to do with whether we can do math with those, right? Typically, categorical would mean, does it make sense to subtract the values? So, for example, with the car example from earlier, well, I can't subtract the color of cars, can I? That doesn't make sense. So that would definitely be not ordinal, right? There's no definitive order to the color of the cars either. I can't say that red is number 1 and a black car is number 2 and green cars are down there at number 7. No, that's not how it works. Right? That's something that, I mean, you might be able to rank your preference in a subjective manner, but that's not really statistical. So I could not possibly order the cars in any meaningful way. And again, you can't really subtract them. You can't subtract red from black and end up with a white car. That's not how it works, right? So that would absolutely be a categorical variable. Just like your phone numbers would also be a categorical variable, because if I try to subtract phone numbers, that's not giving me any useful information. Now, again, we can still have ordinal variables that are also categorical. For example, well, your grades, right? We know that an A is better than a B, but what's an A minus a B? There's no meaningful answer to that question. So we can have order to it, like your grades, A, B, C, D, F. Or, again, sometimes there is no order. And again, it's just one of those things that we want to recognize and be cognizant of every time we see a data set where we start to do some analysis. So when we do analysis, if we're dealing with a univariate data set, which again, remember, just means one variable, we want to focus on 3 things. First, the center of the data, which would be the mean, the median, the mode. Again, typically one or all of those things, or 2 of those things we would look at. That's our center. What is the center point of our data? Then we also have the spread of our data, which is our range, right? What's the smallest minus the biggest? We have our standard deviation, which, remember, our standard deviation, if we have a very small standard deviation, it means our data is very close together. And a large standard deviation means our data is much more spread out. And we can also talk about things like our interquartile range, right? If we do our 5-number summary, the interquartile range is that value between Q3 and Q1. Then we also want to talk about the shape of our data. Is it symmetric? Does it make that bell curve? Can we use the empirical rule? Or is it skewed? Do we have a tail either to one side or to the other? And then we also want to ask about the modality, right? Is it unimodal? Which would mean, again, with the prefixes, does it have one mode? Is there one peak? Or is it bimodal? Are there 2 peaks? And so on. Or is everything flat, in which case it's going to be a uniform distribution? Again, these are all important questions when we're talking about univariate data. Also important with univariate data is making sure that we identify any possible outliers. So outliers are our data points which are extreme compared to the rest of the data set. And again, we can actually define these mathematically too. If we go back to that interquartile range, right, between Q1 and Q3, if we go 1.5 IQRs or interquartile ranges in either direction from Q1 or Q3, and we're outside that range, that number would be an outlier. Now, when we look at bivariate data, we are trying to see if there's a relationship between 2 different variables. Specifically, we want to know if there's a relationship between our explanatory variable and our response variable. Now, the really, really critical important thing to remember here is that even if we do show that there's a relationship, even if we do show that there's a correlation between these 2 variables, that does not necessarily mean that one causes the other. It is very rare that we are able to actually claim that one variable causes the other one to change. The only time we could actually do that is in a very controlled, scientific, designed experiment situation where we have defined control groups and we've reproduced these results several times. Now, that being said, and the fact that statisticians and scientists very rarely are allowed to claim causality, right, that A causes B, that is not necessarily how it's presented in the media. They get their hands on a study with a good correlation, you're immediately going to see that exercising causes you to not get cancer, which is not at all what the study showed, but it sounds good, right? And if you saw that, you said, oh, these exercises are going to make it so you don't get cancer anymore. Are you going to click that link? Yeah. If not you, there's a lot of other people that will, right? So we need to be very careful. And the reason for this is that, again, even if 2 variables show a relationship, that does not mean that they're causing one another. There could be other confounding variables out there that actually help to actually explain both of them much better. So, for example, there is a bunch of studies out there that show that there is a correlation between using sunscreen and getting skin cancer. Well, wait a minute, you say. I thought sunscreen was supposed to prevent skin cancer. You're telling me that the people who use sunscreen get skin cancer more often? Well, yes. Yes, of course they do. Because the people that use sunscreen and the people that get skin cancer are actually part of the same group, which is a group of people that spend a lot of time outside. If you're spending more time outside, you're going to be more likely to put on sunscreen more often, and you're also going to be more likely to get skin cancer at some point in your life. So the sunscreen and the skin cancer are not really related to each other. They're both just related to some third thing, which is being outside in the sun. Similarly, there is a relationship between Lyme's disease cases and drowning. Well, wait a second. Would it make sense that getting Lyme's disease causes you to go drown yourself? No, of course it wouldn't. That doesn't really make a ton of sense. So why would Lyme disease cases be correlated with drowning? Well, the real thing that they're actually correlated to is going to be summer. These are things that happen in the summer. Ticks come out in the summer, people get bitten by ticks in the summer, they develop the symptoms, and they get tested for Lyme disease in the summer. And when do people drown? Well, you got to be swimming first, and typically most people aren't swimming in the winter, they're swimming in the summer. So again, Lyme disease and drowning are really both just related to it being summertime. And that happens a lot. And it happens really frequently in medicine and the social sciences too, that we see these two things that are related to each other. And again, it's a great jumping off point to do more research, but that's not always how it's presented. So again, we need to be responsible because we are good at our jobs and we are ethical and we follow a certain moral responsibility to be good citizens. But, you know, not necessarily everybody in the news business feels that way when their jobs rely on them selling advertising and getting clicks. Oh well. Now, to review tidy data. So, all of our data in R, we're typically going to be dealing with what are called data frames, or sometimes tibbles. And we have our 3 rules to make our data set tidy. First, every variable needs its own column, every observation needs its own row, and every value needs its own cell, kind of like a spreadsheet. So, for example, if you are someone looking up, let's say, football statistics, and you have your table, right? And each row is going to be different players. So let's say like Saquon Barkley, right? He's one of the rows. And then as you go along the row, there's all the different variables, which would be rushing yards, rushing touchdowns, receiving yards, receiving touchdowns, those sorts of things. And so each variable is going to have its own column, and then each player would have its own row. That's tidy data. When we explore our data sets, and again, it's a good idea to do some exploring our data set before we do any in-depth analysis. As we load our data sets, again, particularly from packages on the internet, from the CRAN archive, there's going to be descriptions about the data set and the purpose behind it and the motivation behind even creating it that comes along with that package. And so the easiest way to understand or see what is in there, you do question mark and then the name of the data frame in your console, and then it'll pop up in the help window with the description. Also, we want to look at things like using different functions. So the head function, head, and then again, we apply that function head to our data frame by putting the data frame name in the parentheses. That looks at the first 6 rows. So again, it just gives us kind of a snapshot of the beginning of our data frame so we can get an idea of how it's organized and what it looks like. We can also count the number of observations, which would be the number of rows by using n row, again, on our data frame, or the number of variables, which would be the same thing as our number of columns, which would be n columns, again, on our data frame. If we load our tidyverse package, we can also use the glimpse function, where again, the glimpse function is going to show us each of the columns and how the data is stored in each of those columns based on the different types of ways we can store data, like integers and characters and that sort of stuff. So again, that's another good starting point to get a handle on what is going on in your data frame. All right, so to wrap this up, can you answer the following questions? Question 1, which is a 3-parter. If I had a data set about the number of kids that different families had, all right, so again, my rows are going to be the different families, and one of the columns on my data set is going to be the number of kids in each family. All right, and that is the one column that I want to look at. So first of all, would that data, if I'm looking at the number of kids, would it be quantitative or categorical? Is it a number or is it going to be a quality? All right. B, is our data going to be discrete or continuous? Which I guess actually answers part A already, right? If you didn't get the right answer yet. So if it's discrete or continuous, right? Can there be a part of our data, right? Can you have 2.75483 of our variable? Or would it have to come in whole numbers? And then part C, would our data be univariate or bivariate? Am I exploring just one variable or multiple variables? And then question 2, in a tidy data frame, what would each row represent? All right, well, I hope we learned something, or at least reviewed and brought things to the forefront of our memory. And as always, take care.